When volume levels change, we might expect that the audio just becomes more or less loud, but besides that remains the same for our ears. However, our perception of loudness is a bit sophisticated, and this can be easily shown in terms of tonal balance. Experiments with pure tones show that our hearing is frequency dependent, as usually visualized with Fletcher-Manson curves or equal loudness contours. In addition to being frequency dependent, the ear response to amplification is also nonlinear. In order to show that, we can draw sound pressure levels versus perceived loudness for different tones. For a 1 kHz tone, it should be something close to the following curve. To make it easy to compare the values, we choose the scale in which each grid cell corresponds to an approximately 2 times increase in both pressure level and loudness. For tones of different frequencies, 100 Hz and 200 Hz, we get two different curves. We can easily see that when these tones have the same sound pressure level, they are never equally loud. 100 Hz and 200 Hz are always quieter than 1 kHz, but the difference is less prominent for high levels. We can also see that if we have three tones that are equally loud at some signal level, they will never be equally loud at another. The more we change the volume level, the more we stretch tonal balance of the audio. The conclusion is that there is only one perfect volume level at which the audio is meant to be played. Normally, this is a quite high level, which is not always possible or enjoyable. And this is where loudness control comes to play. It compensates perceptual difference of tonal balance at different volume levels. The ideal loudness control should change the loudness equally for all perceived frequency components. Considering all this, we can design a basic digital loudness control as follows. First, transform the audio into frequency domain using FFT. Then calculate correction gains for each frequency bin, considering target and actual volume levels. And finally, reconstruct processed audio using inverse FFT. Gain calculation routine should consider basic psychoacoustic principles, namely energy of critical bands, equal loudness contours, and subjective volume up response. I appreciate your listening to the following processing sample that shows the modeling result. But first, please adjust volume of your speakers or headphones in order to match hearing threshold of the model. You can listen to more samples if you like, watching a separate video on this channel.